And I know we're gonna have some people chiming in here. There's gonna be a lot of people coming and attending today, so.
I hope
I'm looking forward to it because I don't know much about, when we used to do machine learning back in the old days. We used to, you know, we used to do programming and stuff. It was very simplistic, but today, I mean, the field has gone crazy. This is the hot topic.
And here's the crazy thing. I think you have been doing machine learning. We didn't call it machine learning. Anytime you did regression or classification, you did machine learning. It's just data is more ubiquitous now. These libraries are more available now. And the terminology is a little different because it went to the, you know, computer science field. They named it, you know, they call it function hypothesis. Now you tell me why, I don't know. But you know, one of the concerns that I have once in a while is that this is making us dumb, like, because we don't really have to think all that creatively. It's just a melting pot. We throw in data and say, well, does it work? As opposed to the more careful approach to modeling. Now, anyhow, but those are thoughts. I hope the talk goes well. I organized this a little while ago when I was giving a talk at University of Cincinnati, and I cut out a bunch actually for today's talk because I figured it was too much, and I added a little bit on our new work. But it's more of a high level, going through a few pieces of work. I wonder how. Yeah, I don't know how it resonates with the audience, but just to hopefully prompt discussions.
Yeah, if you could go for about 40 minutes, somewhere thereabouts, and then we'll open it up for some questions at the end. There may be some people that have to leave at 3:50 p.m. simply because they have classes to get to, or they have to get their computers ready for a Zoom class. You know how that goes. You're on this every day, so you know.
Actually, yes, I am the host of our colloquiums this year, and the chair. Yes, it should be. I should be able to finish it by then. Should I try to share my screen now, or are we still waiting?
Mike could help you. If you share your screen, I'll be able to get you over here. I could switch you to the main computer monitors here.
I mean, it is telling me if I stop sharing that it will stop your sharing, which to me sounds fine. So I will go ahead and share my big screen. And these are my slides. So now.
Oh, yeah, you're showing up. You're showing up.
And I can go through this just so that, oh, the quality on this is low. Oh, well. And I have a few videos that I want to quickly play and make sure that yeah, the videos are playing. This one's playing. This one also was playing. Good. So, and this is a YouTube video which I'll perhaps not play, but just in case, yeah. All right. Okay. Yeah, I think things look. You only see my slides, right? No notes. I mean, I don't have notes on, but it's on presenter view.
Yeah, I could see your slides. We'll see if everybody else sees them.
All right, I'm gonna get some tea or coffee if you don't mind, just in case I start coughing. And for a second, I'll stop. My microphone is set to the correct one. I've got my speaker set. All right, things look good.
You got a beautiful background there too, Boulder.
Oh, thank you. That's very kind of you. It's obviously fake, and I don't know how well. Also, I see my shirt showing really weird because of the pattern. I wonder if that's how you see it too, but I look like
a little bit. It's not so bad.
It's funny because of the stripe, I think. But do you know Andrew Carlton at Penn State?
I do not.
He's a professor of climatology. He's in geography. Very, very senior. He did his PhD here at CU Boulder in the 80s, I want to say. And this is a photo from there. So you see the old school cars.
The only person I used to know from Boulder, Colorado was Gary Gale. He used to be there back in the 90s, a long time ago.
Yeah, and Andrew only did his PhD here. I think So faculty at I think you Indiana, Bloomington, and then Penn State. He's been there for a while. All right, I'm gonna get something to drink just in case I start coughing. Okay, this is a computer, so.
So it's all just on the screen.
It's the end.
So it must be a different.
Hello there, Pete Whalen.
Hey, Tim, how's it going?
Good, how are you doing, sir?
I'm doing well, thanks. Yep, good.
Always good to see you.
Good to be here still.
I see you're on campus.
Yeah, I'm hiding here in the in my room today, and office hours this afternoon. So I stick around here to be educated, to learn something here. So, yep, on campus.
Well, this is going to be an interesting talk. I've been looking forward to this. I wanted to learn more about machine learning, so.
Yeah, it's time for us old guys to go back to school, huh?
Absolutely.
I hope, oh God. Prepare to be disappointed.
Oh, no, that can't be true.
Right. No, I just try to keep it high level and not teach machine learning, but instead how and why we may need the interactivity in it. But anyhow, happy to, you'll know in an hour.
Okay, well, we look forward to learning something. For goodness sake, you got to be able to teach some people who know nothing. You got to be able to give us something.
Thank you. I guarantee you, it's going to be better than your office hours.
All right. Okay. Yeah, that was good. That was pretty hot stuff. Yeah. You won't be asking me any questions, so I'll be okay.
There you go. So some faculty, or I guess the department are on Zoom, and then it's broadcast on YouTube separately for the public. I think that's a good idea. That's a great idea.
The YouTube link is on a 20-second lag.
Yeah, that's right. We also host, I mean, I host our colloquiums this year, and I do the same thing, but everyone calls into the YouTube, which has not been very interactive, and we haven't had face-to-face discussions.
Okay, it's 3 o'clock. Welcome everybody to the Department of Geography Colloquium Series for 2021 spring. It's going to be a fantastic talk today. We have a guest out of Boulder, Colorado, Morteza Karimzadeh, who is assistant professor in the geography department, the University of Colorado at Boulder. Very beautiful campus. He holds a Master of Science in Geographic Information System from the Tuesday University of Technology, Tehran, Iran, and PhD from the Geography Department in Penn State in Geographic Information Science. His expertise is in data science, geographic information retrieval, and visual analytics. And we are very pleased to have him with us as a guest speaker today for this colloquium series. Morteza, take her away. Thank you very much for being here.
Thank you so much, Tim, and thank you everyone for having me, giving me this opportunity. It's really great to be in Florida in spirit. It already feels warmer here. Honestly, I don't even know how cold it is outside. I did not step out of my apartment. And why would I? I'm really glad to be among you all. My talk today is entitled Interactive Machine Learning and Labeling for Heterogeneous Geospatial Data. Now, I added that labeling after I sent in my title because I feel like that better captures what I'll be talking about today. Before I get started, let me just say that you'll see a lot of interfaces and engineering and work and multiple projects, and these are all collaborative work with folks at Purdue University at the time. David Ebert, who was my supervisor at Purdue University, he's now the director of the data science program at Oklahoma University. My colleague, Hamidreza Zoraghian at Population Council in New York City, and my graduate student here at CU Boulder, Behzad Wahedi. So again, lots of work. I did want to first give credit where credit is due. But for the rest of the talk, I'll just focus on the substance. We are all here, and I feel like I don't necessarily need to make a case for machine learning. I'm not saying it's the solution, the panacea, and problem solved. That's what everyone's got to do. But I think there is this awareness that we need machine learning for certain tasks today, and we can really take advantage of it for our analytical, predictive inference tasks. This is a paper we submitted 3 geographers. So perhaps you can send a copy to Governor DeSantis. But we sent this to Nature Communications. It's under review, so too early to see how it goes. But it's for county level, it's on county level prediction of new COVID-19 cases using spatial temporal machine learning, right? So we use social media data and human mobility data to look at people's movement and connections. And surprisingly enough, and we did not really expect this, Facebook friendships can be used to create really predictive features on how COVID-19 spreads. I guess it's all about who you're part of it, not necessarily where you move to or from, as observed by your cell phone. And really the concept of our model is very, very simple. It's we took what we knew in spatial temporal modeling, and we've been doing in quantitative geography for years, and looking at the spatial temporal lags of how many cases you're seeing this current week in your county, how many did you see last week, how many did you see 3 weeks ago, and the same for the counties that you're connected with. Now, connection here is not necessarily geographic contiguity, but also the strength of connection as measured through people's movements and Facebook connections, social media connections. And this was a rather unexpected result that we got, that our models actually perform much better than what the CDC uses today in their reporting. So the way it works in the US right now, there is this COVID-19 forecast hub, which is a collaborative effort of, at the moment, 32 teams submitting their models. Again, on any Monday, they say, well, we'll have this many cases in this county, in any single county, essentially, next week, in the next 2 weeks, next 3 weeks, and the next 4 weeks, using the historical data that they have up to that point. And then the forecast hub uses an ensemble, a combination of those predictions to then make a report. So when you go on CDC's website, that's the number that you see, right? Our models, again, relatively simple tree-based ensembles, using spatial temporal lags, temperature data, socio-demographic data, without any epidemiological modeling, essentially, is doing much better. So the dashed lines here are the mean absolute error of our models for the weekly forecast, as well and we are comparing that to the continuous lines, which are the ensemble models that the CDC uses. So you see that the first week predictions are more or less the same. In fact, our model are not as good as the CDC ensemble, but really 2 weeks ahead, we are much better. 3 weeks ahead, we are much, much better. And 4 weeks ahead, we are absolutely better than what the CDC uses. And we did look into, well, why are we not doing as great in the first week? The difference is very small. And we just, in consecutive weeks, we realized, well, some states are just testing and reporting with lags. You even see the boundaries of some states standing out in the prediction error. You have Texas here, you have Georgia, and then you also see Kentucky there, perhaps the boundary standing out. And when you look at the next week, you'll see the exact opposite of this error pattern. So where we had underestimation, next week we have overestimation. Now, this is a talk of its own. Sorry to give you just, for the very shameless self-promotion. It's a colloquium talk after all. But I wanted to give you an idea about, well, how can we use the concepts that we know from compartmental models of, SIR, susceptible, infected, recovered, and take that and put it in a machine learning model and get better results. So they are promising. Now, what was key really here, obviously, that our models did what they did because they could look at historical data. What is that historical data? That's essentially a training data set, right? And you can chunk out a piece of it and say, well, let's assume I didn't see what I saw last week. How would my model predict last week? That will be your testing data. So for supervised machine learning, you need training and testing data to then train the parameters of your models. It's a very data-driven approach. And the parameters that are in your model do not necessarily connect to the domain, right? As opposed to, let's say, the SIR model, the traditional epidemiological model that looks at susceptible compartments of population, the infected compartments, and the recovered parts, and says, oh, well, we have this many people susceptible in this county, and the reproduction number of the disease is this much, therefore we'll have this many cases next week, right? We don't have a concept, at least in our model, compared to that reproduction number, right? But our models are doing the predictions directly. So I hope you're all on the same page that, especially in supervised machine learning, training and testing data that are labeled. By labeled, I mean when we have the ground truth available to us is key to getting results. There are unsupervised methods too, but almost in a lot of cases, even unsupervised methods are a pre-processing step, so to speak, for a supervised method, in which case you still need to have ground truth data to see how good your models are doing. And that is kind of my focus today. How do we make sure we have that kind of data? How do we make sure that whatever data that we create and label today is relevant tomorrow? And the machine learning model is only as good as your data. So take a look. This came out a while ago. Twitter deployed this algorithm on its tweets that's saying, well, if you upload pictures, it will go and find a thumbnail in it to focus on the face in that picture. And people immediately started testing it, right? They uploaded this picture, this elongated picture with McConnell on top, Obama on the bottom, and the other way around. So these are two separate pictures uploaded to this tweet. And guess which face the Twitter algorithm picked as the thumbnail? Well, the white face. And they changed, folks played around with it a whole lot. They changed the tie color, the suit color. It always picked the brighter, whiter face until they actually inverted the color, in which case Obama would come up because now he had the lighter skin. So why did it happen? Whatever algorithm they were using for face detection, facial recognition, they just tends to prioritize faces with lighter skin. So it's cliche, but really your algorithm is going to be only good, your model is only going to be good as your data. And that's where I think what we have been doing for years is, I think it has a lot of potential. And that is visual analytics. Yes, it does take a bunch of engineering and patience. And it's an expensive effort, but perhaps worthwhile. So what is visual analytics? It's the science of analytical reasoning facilitated by interactive visual interfaces. And really what it is a bunch of backend models and algorithms, databases, and you have your data sources, be them novel or traditional, and then these algorithms and data are kind of cooperating with a human user, whether it's a decision maker or an analyst, whether it's an expert user or a novice user, to really use these algorithms to make sense of this data, to do something with it. So visualization is not an end goal here. I'm trying to simplify things here. It's not as if cartography is always simplistic visualization, but really the difference, if I have to explain it in simple terms, of visual analytics versus visualization is that it's a start to the analysis. It's not the end. It's not as if you generated a model, now you have a story to tell, so you create a visualization. And it really helps us incorporate human knowledge into computations, into the imperfect models. In the case of McConnell picture, why did we even need perhaps a facial recognition algorithm? Maybe let the human user do it, or maybe let them have control over the algorithm. And it helps us make our research really impactful and available to users out there. And I'll show you an example today. So from here on, my talk is going to be a little disconnected. I tried my best to kind of splice it up, but I'll show you 3 different application areas for this approach of visual analytics with machine learning, with interactive human involvement. The first one is social media analytics using social media data for situational awareness. Then a more technical part for geographic information retrieval, and I'll move to Spambot labeling, and I'll touch on what we are going to do with this approach with our new project. For each of these, I'll try to make the case a little bit as to, well, why either of these projects, but that's not really the focus of my talk. The focus is mostly on the methodology and the line of thinking that goes behind interactive learning and machine learning. So the first things first, social media analytics for situational awareness. So we in geography haven't been using textual data all that much compared to the amount of efforts and resources and research that we have put on other kinds of data. The reality is 80% of all the data out there is textual. That's more or less of anecdotal, an anecdotal quote, I want to say. It's not empirically been tested from what I gather. But you see text everywhere, academic articles, right? Right now you have all these smart systems that learn and understand text and answer your questions every time you Google. Well, all our knowledge is sitting in those academic articles, including geographic knowledge, legislation, news stories, social media. The very phone that you interact with every day, you're communicating with it via text. And this one we know, this is empirically tested, that 80% of all of this textual data is in fact geospatially referenced. There was a paper that went out, folks, Hallman and Burgard, they went out and tried to confirm this anecdotal code, and they saw that yes, 60 to 80% of the data, depending on how you measure, on Wikipedia articles, does in fact have a geospatial component. But we are not really being able to harness it all that much because it's such a noisy data source. There is so much in there and it's just not structured. That's thus the word unstructured. So the next couple of applications that I show you are geared towards this. How do we find and synthesize and visualize salient information in large amounts of noisy text? And how do we geolocate text? Not just from place, but also text that is about a place, right? That is the difference between explicit georeferencing and content georeference. When in explicit georeferencing, you have, let's say, your tweet tag or your news deadline, as opposed to the place that your news story or your tweet is about. And then I'll tell you how exactly we use interactive machine learning to solve each of these problems, where the pitfalls are, and how it can be improved. So let me move on to my other slide. Taking a step back, situational awareness. How is it usually done out there? You know, if you go and find your campus's emergency operations center, you'll see that there are perhaps maps on the walls, and there are big desks and lots of papers, and calls are coming in, papers flying around. And there's always a bit of a lag and delay between information that comes in and when it's digested and the action that goes out. Now, American Red Cross, US Coast Guard, all sorts of organizations tasked with first response have been using social media in two ways. One is to see, well, what's going on the ground? Can we identify useful information and act faster than waiting for that call to come in? And the second one is, how can we put useful information out to prevent misinformation and to really inform the public? And there has been multiple studies and success stories out there. When I was at Purdue, prior to joining at CU Boulder, I was a postdoc at PERVAC. And we had a large lab, and I had the privilege of leading a relatively large group of students. We were working on this toolkit called Social Media Analytics Reporting Toolkit, SMART. And it's a tool set that harvests the social media data and allowed the first responder to look at the content in geo-visualizations as well as visualizations and really make sense of what was going on. Now, if I zoom in this picture, you'll see that a hurricane's moving in. It has hit one area, it has missed another one, and it is expected to go somewhere else. And people are talking about it exactly as such. And they are reporting as to what they are observing in their let's say, local settings. Now, this was a very popular toolkit. Multiple organizations around the country tasked with first response, they wanted to use this. So we had this privilege of working with first responders firsthand, really improve this toolkit for them. And what it does, again, it takes in the user specified filter from the first responder. I'm interested in the fire scenario or a heat wave or a flood. And it had geovisual analytics interfaces, and it still does. It's just that I don't work on it anymore, by the way. And spatial topic lenses. This is essentially a natural language processing made specific for a geographic interface for topic modeling, nothing that complicated. And word clouds really helped the user to understand the trends, what topics were trending in social media for their I guess, domain of interest, as well as anomalies. What's new? What is unusual that's happening, comparing to a baseline? If I redraw that geovisual analytics chart for this tool set, so the data was essentially social media data. It was big, lots of engineering to harness it. We had back-end natural language processing models, spatial topic model, and spatial indexing, and then we had interactive interfaces for the first responders to make sense of this data, right? We had one problem, however, and as much as we tried, this is where out of those 70 organizations that use this kept coming back to us and says, we really are seeing a lot of noise, right? It's great, we want to use it, we'll continue to use it, but can you help us with this? And that's what got us thinking that a one-off model, a one-off tuning is not going to help this diverse set of users, right? We have a lot of irrelevant text. We want to reduce those in the visualizations. And we want it to be dynamic. One flood that hits here perhaps has other keywords that are relevant to another flood that hits in another region. One wildfire is different from another one. Also, again, one person is looking at a wildfire event, one person is looking at a hurricane, one person might be looking at a terrorist attack, very different domains. So our solution was to try to interactively incorporate their first responder knowledge as they are doing the analysis. And that's where interactive learning and labeling is coming in. And the idea was to see, well, can we use linguistic context in the text itself to see, well, what's relevant? The entire apartment is burning down. That's perhaps relevant to a wildfire story, but Bernie feeling the burn is perhaps not relevant to your wildfire story. Can the first responder just do a little bit of interaction with the system and train the system to be able to identify these as such? So our solution, in fact, if I look at it today, this is only a year and a half old, maybe, and it still feels and it already feels out of date. Is first to take the sentences and the words and then convert them to feature vectors that you can use in algorithms to train a machine learning model. We use pre-trained models that I'll be happy to go into more detail if necessary, but really these pre-trained models are published by usually search engine companies. The word vector for different words and concepts actually help us understand the semantic space better, and therefore the algorithms will work on those. So the difference between Denver and Colorado in the vector space is similar to Indianapolis and Indiana, right? The capital to the state. And you can take your tweets and sentences, feed them into this pre-trained model, and then get the vector as output. My house is on fire will result in such vector, for instance. I'm showing 3 dimensions here. Really, we use 300-dimensional networks. And then tweet comes in, goes through this conversion. We get the vector matrix. This is the part that we developed, right? And the idea was, can we have a machine learning algorithm, in this case, a neural network, a very shallow one, in fact, not a deep learning model, that goes and guesses which one's relevant, which one's not relevant, generates a label, right? And then let the user decide if it did right or not, and then take the feedback from the user. So just as simple as that. This built in to the system, and a shallow network, thanks to smart modeling of the vectors, worked relatively well. Well, obviously, initially, this system wouldn't know much. But as the user goes and says, this is relevant, this is not relevant, this will start learning. And for each scenario, we'll have relevant tweets. So the idea, again, was not that, hey, we have a dump of data sets at home and a bunch of tweets, let's train on those, and then let's deploy the model for the user. The idea was to let the user refine the models as they were working with the system. So the way we evaluate the system was essentially a simulation of that process, saying, well, let's iteratively train this model with every 10 new tweets plus 100 previously labeled to simulate that live use of the system. And we compared a few very simple neural network. These are literally like 3 lines, perhaps each, in a TensorFlow framework, and we looked at and see, well, which one's both good and is fast enough for our use case. So not only we looked at the F1 score and the accuracy, but also how long did it take for it to be trained so that we can use it. And we saw that, recurrent neural networks and LSTM that are usually used with natural language processing, they work well, but they take forever. So we used a simpler one. We compromised a little bit, and it worked well in the interactive setting. And by the way, you might be asking, where do you publish these? So there is the IEEE Transaction and Visualization and Computer Graphics Journal, as well as the Viz conference that has structure on how we report on these kinds of coupled human and algorithm systems. Cartography in GIS is another journal. In fact, the editor, who might be in the audience, as he told me, he also reached out and said, we are interested in the visual analytics work. So there is room for it. But we also computationally evaluate our models. So you might be asking, well, how good are these? So with every incoming batch of 10 tweets, we calculate the F1 score on 3 data sets that we had labeled only for our testing purposes. These are not used to train a model, deployed in the field, and say goodbye. This is only to see, well, let's assume we have a wildfire scenario. How good are is our algorithm? These are a bunch of tweets that someone had manually labeled as related to wildfire or not related to wildfire. And you see that around 228 tweets, the accuracy, actually, the F1 score kind of stabilizes around 71%. But even before that, only around 50, 60 tweets, it makes all the difference. And it really reduces a lot of noise in the context of situational awareness so that you don't see random unrelated tweets on your screen. And we tested it on other scenarios as well, NYV and New York train crash and bus bombings. These are labeled free data sets that are out there. And this is just an example of how the results look like. As you see, by the way, tweets are anonymized. These are not for any individual person. These are for situational awareness, flyby of what's going on the ground. So only after 20 clicks saying relevant, not relevant, the first responder has done this and then sorted the tweets by relevance. And you see that the table on the left, almost all tweets are related to a weather event, let's say hurricane, and the one on the left are absolutely relevant and labeled as such. These are the labels for relevance, and the red labels show that these are not irrelevant. And again, lots of engineering, two students working on this at the time too. It was not all my work. Let me transition to the other part of this, and that is the geo part. Well, I've not been really talking about the geo part of text, which is kind of my expertise too. And really our idea was, well, can we use where this textual data is referring to identify, what's relevant, what's not, what do we show in our visualization. Now, only 1% to 2% of all tweets were geotagged. This is at the time, by the way. Things have changed in just the last 2 years, significantly. But 35% at the time when I analyzed did have a place name in the text, and 50 to 60% had a user-listed place name in the profile. So the idea was, can we take advantage of this and try to even refine our system a little better? So we wanted to incorporate this geoparsing approach into the toolset. And what's geoparsing? Detecting place names and putting and mapping them essentially. So Boulder is surrounded by townships with ambiguous names. Boulder is a place name. It has a unique ID in our geographic dictionary as well as geographic coordinates. There are tool sets for doing this, especially for actually detecting and recognizing Boulder as a place name. That's called name entity recognition. And then the difficult part is really this disambiguation, which we also refer to as toponym resolution. I want to say this, we are pretty much where we were 5 years ago in terms of the accuracy of this, more or less. It is a very difficult problem to solve. And that's why you're looking at Columbus, Ohio. Just looking at these names, you will perhaps understand, well, mutual, first of all, is a name of a place. And you've seen these places elsewhere, right? Newark, Africa, New California. Dublin is a very well-known neighborhood in Columbus, Ohio, and kind of an upscale one, right? So these are not random unknown places, and you see names as such. And disambiguating this is no easy task. This is Boulder, Colorado. Well, the Denver Front Range area where I live, and all these names should sound familiar to you, and perhaps this one, Tampa, right? And we also have these kinds of names, hygiene. When we talk to people, no one is surprised that we have a place, hygiene. People live in it, but you're probably surprised. And there's also a place called Last Chance, which is your last chance to get gas and perhaps use the restroom if you're going towards the plains eastward. To give you an idea of how ambiguous places are, we have only 88 cases of Washington in the 50 states within the United States. Now, some of them are derivatives, some of them are physical features, mountains, rivers, and a lot of them are actually populated towns. So we were trying, and this was a difficult problem, and we needed a training data for the automated algorithms to detect place names and then geolocate them. So I developed this interface, and this was a relatively painful experience. Now we are looking at an academic article for geolocating the title and the abstract. So the idea was, well, can we train an algorithm that does a guess? Well, what are the place names? Where are they located? And then let the user correct those on the map as well as in text. And then once in a while, the algorithm gets updated the same way as I showed you with the other application in Smart, and then make better suggestions. And then we take these labels to have better models in our systems. Now, as you can see, we are doing documents more or less one-on-one, and the context of each document is unique to itself, and it's just a very painful, laborious process, as automated as we have made it. And that's why, folks, if you're doing a PhD or graduate school, you shouldn't be doing data labeling. It will take forever, perhaps. Some advisors may be mad at me here. I'm just saying, realistically, this is the kind of information that we need for better models. And again, if you're sitting in a funding agency, this is where we can contribute to science in a long term rather than that one model that we create. Someone else walks in, makes a better model if we have good labeled data for machine learning. As you see, again, this worked, and we trained a geoparsing system. I published a few papers. Not only that, before my papers were published, Alexander Klippel in Penn State was really interested in just studying the place names themselves and their characteristics. And a bunch of digital humanities use cases that approached us and said they were very interested because they wanted to generate their ground truth data themselves. They did not trust any labeled data coming from any other field. And it culminated in an automated system, in an API that was online. You would feed in text, you would get place names and then geographic coordinates out of it, as well as a bunch of other attributes. And it enabled research really because we made it available. Other folks, I was only involved in this one. As you saw at Purdue Smart, that's how some of these connections were made, and I was later on hired at Purdue University. But other folks use it in other applications for geolocating text. But again, and a PhD dissertation by Sam Steele. But remember, this system has been collecting dust for a few years for geolocating text. I'm not referring to, so by the way, other people's system. I'm referring to this. The reason is, well, the training data was limited, and it will only work well if people who are using it have similar kinds of data sets that compared to the one that we trained this on. And I'm going to use that to transition into the third application that I promised I'll show you. And this is where I feel like we kind of nailed it, thanks to Moussa Khayyad, to let this work for Spambot labeling. So the idea was, we really don't want to label things one-on-one. That's painful. That takes forever, and it's expensive. This work itself is not geospatial, but I will show you how and why I'm showing it to you and how I'm going to use it in a geospatial domain. So another visual analytics application for labeling Spambots. This was also published in IEEE Viz and the TVC journal. Let me motivate it first. After everything that this country has been through in the past few years, perhaps all of us are on the same page that social media is a cradle for misinformation and disinformation. Now, one thing that you may not know as much is the amount of unreal accounts, the number of unreal accounts that are on social media, right? So these are 2016 studies that show you 40% of all the accounts that you see on Twitter, for instance, are spam, are not real. And they manipulate public opinion. They're part of campaigns, very targeted ones to change public opinion. Sometimes they just want to make money or do malicious attacks. It has been a topic of research for a long time on how to detect spam accounts. Now, whether social media companies are really acting on it, that's another question. I'm really not in a place to answer that. But most of these previous studies, what they did was create an automated model and try to identify spam versus not spam using machine learning algorithms usually. But again, they had that same problem that we did, was that you can't just create one training labeled data and then say, well, we'll be fine. Guess what? These Spambot campaigns change their behavior. They spoof algorithms. They become harder to detect. And depending on the target they have, they constantly change their strategy. This is especially harder that some of these are combined spam and human spam bots, so to speak. So it's really hard to maintain representative training data sets, and it has to be done frequently. And that's why we thought about, well, let's do a visual analytics solution in which we can actually update our training data set faster. And it had a bunch of linked in UI components that will help the user label the data easier. So this is the overview of the tool set. These are the individual visualizations. In this one, you can see a timeline. So we can see the accounts posting in the timeline in any specific year. You could change it to month or day, and then try to, you can label in any of these views. Green refers to genuine account, Purple refers to spam, and blue means not labeled yet. Let me take a step back. I mentioned this here. We want a visual analytics approach to maintain a representative data set, but also we don't want to do this individually. That was another motivation. We want to batch label the accounts and then fine tune. This is perhaps the view in the tool that is one of the most useful. So each tweet, each Twitter account comes with a bunch of attributes. How many followers, how many tweets, what days did it tweet, how long are its tweets. You can directly observe a bunch of features, as we call it, or derive them. But who has the time to look through all of those? So why don't we map them in a 2D visual interface using dimensionality reduction algorithms? There are well-known ones out there, and see if the spam ones cluster together versus the genuine ones, and they do in fact. And then we start our labeling from there, saying, well, all these tweets that are more or less spam will be labeled as such. All the ones that are genuine will be labeled as such. And if something stands out, let's go and try to fix it. In addition to that, we can look at each Twitter account and their tweets, as well as their word clouds individually, so that we don't miss out on the ones that do not belong into any cluster. Now, you might be asking, well, if we batch label, some genuine accounts may end up spam. Yes, but again, this is an algorithm that is able to absorb noise. Then the idea is not to have here a perfect training data set, but good enough compared to what is being used out there. It's literally can be improved the state of the art. As well as topic modeling. Again, we are looking at the polarity and the subjectivity of the tweets of any specific account. That will tell us something about whether these are Spambot batches or genuine user batches. I'm going to skip the feature explorer view just in the interest of time, but just show you an example. The user is starting at the timeline, looks at clusters of Spambots and genuine accounts and labels as such, both in the timeline view as well as that clustering view. As you can see, the dimensionality reduction view. This one tweet that they clicked on, as you saw, does not belong to any cluster right here. So they went in and they looked at the account itself, the tweets themselves, the words, and see whether they should label them as Spambot or genuine. And again, how do we publish this? We actually evaluate the system, both the algorithms as well as the user interface, and looking and seeing, well, how well the system did in terms of accuracy and precision and recall. Our system did better in most categories, much better in fact, not as much in precision compared to manual, because you're doing batch labeling. So you may include some that are not correct. It still did better than doing manual one-by-one labeling when a human expert is looking at each account. But one thing that users really hated about our system was how difficult it was to use. We really didn't refine it. It had too many features and too much latitude and freedom for the users. But that's what you do when you develop a software platform for experts, and you have non-experts in the user evaluations. It's not very surprising, but we were honest with it, and reviewers appreciated that in our review. I'm going to transition to the last part of my talk now. I showed you. Sorry, I'm going to go back in my slide. This and says, well, we have all these features. Let's bring them into the latent feature space. Do dimensionality reduction, and try to batch label things in the feature space to have more efficient labeling. So where I have taken this in collaboration with the National Snow and Ice Data Center at CU Boulder, as the video is going through, I'll talk through it, is to take this approach for sea ice classification and mapping. Now, sea ice is an important component of climate change. It's also becoming more and more important for Arctic navigation as you have the sea ice melting sooner and freezing later. And in 2020, I believe, if I haven't looked at the updated records, but was the second lowest on record in terms of the sea ice extent at the freeze up stage. So things are changing rapidly, and our methods for mapping and classifying sea ice, especially in the Arctic, are relatively arcane. There is a human analyst sitting in the National Ice Center, which I believe is a subsidiary of the Navy, and then draws maps using SAR imagery of where we have first-year sea ice, where we have multi-year sea ice, and the ice thickness and concentration. So in a proposal, now I think I can, this is a NASA video, I'll be happy to send to you. I just wanted some visuals. This is a project that we did win an award for from NSF, and I'm really excited about this. And perhaps a lot of you are too, in the sense that, I don't know how bored Spambot labeling got you, but this might excite more of you, is using big geospatial data, including SAR imagery, that's an image, two-dimensional, let's say, and altimetry tracks, these are tracks, the LiDAR points, and combine those using machine learning. But really the problem for that combination and using it, other than they're huge and it has to be done in the cloud and all of that, is that we don't have labeled data for these. Again, remember those very rudimentary labels from the National Ice Center, they don't look at the ISAT-2 data. This is a new satellite. It's been up there for what, 2 years? And we want to associate these labels together and do machine learning for high resolution spatial temporal mapping of sea ice. To complicate things, sea ice is also moving and drifting. I'm also stressed how to deal with that. I don't have an answer for you, but we will figure it out. This is just the start of our project. But same idea. Can we do batch labeling in the latent feature space and the SAR imagery as well as the altimetry? Now, the crazy part is we have a talk coming up at the National Snow and Ice Data Center. Unbelievable that the National Geo-spatial Intelligence Agency, they just started doing this exact same thing last year. Very same approach for the very same application and labeling in the latent feature space, which on the one hand, it's great if we could collaborate. On the other hand, I think it also shows the validity of this approach. I know I showed you Spambot labeling, and that was not just spatial, but we can take that and bring it for our geospatial analysis, predictive, and inference tasks. So it was a rambling talk. Thanks for putting up with me so far. Let's talk generals a little bit. You've been doing machine learning. Anytime you use the regression algorithm or a classification algorithm, you have done machine learning in the past 20, 30, 50 years. We didn't call it as such. Why is machine learning a new field? Well, it became formalized in computer science with certain terminology. There are really easy to use software platforms and libraries now, if you knew a little bit of Python, to take advantage of it. And data is ubiquitous now. So we have labeled data for training supervised machine learning algorithm, and lots of unlabeled data that you can take advantage of for unsupervised methods. So how do we take advantage of these new technologies? First of all, we have graduate students, undergraduate students. We got to teach them, and I am doing it. I started offering a machine learning and machine learning and geospatial data course in our department as of last semester. And I was wondering how it would go, especially with the pandemic and teaching over Zoom, and a lot of folks coming in not even knowing Python, but we want to teach machine learning to them. And I think it was a success story. Now, maybe because I had more graduate students taking that course rather than undergrads, but even undergraduate students who could hold on and didn't drop the class, and I'm talking about 80% of them, let's say, they really enjoyed it and they could catch up. They did a project in machine learning in the end too. I honestly wanted to just make this talk about that class today, but Tim convinced me otherwise, and I'm thanking him for that. And the other thing we need to do is to really import these techniques from other domains. We can export right when it's time. I go back to my first slide of predicting COVID-19 at the county level, right? I am no epidemiologist, or, while I'm an affiliate courtesy appointment in computer science, while I have worked with the computer science department, I'm still a geographer. That's how I identify it as such. But we published, hopefully it will be published somewhere after rejections and revisions on COVID-19 predictive modeling. And really the contribution of that work for me as a geographer is not the prediction of COVID-19 cases, is how we actually incorporated spatial temporal lags in a machine learning platform for improving the outcome. The other note I want to make is deep learning is not the end, right? deep learning is very data hungry. For you to train a model, you need labeled data to train a bunch of parameters that make your models, right? Weights and biases and you can think about, let's say, parameters of a linear regression model, right? There's not as many, but in deep learning, you're talking thousands. If you only have, let's say, 2 layers, now add 3 layers and 500 nodes, even worse. A lot of our work in the geospatial sciences, we don't have that kind of training data to work with deep models. In fact, even in computer science, it's not as such. That's why you see a lot of these advances in deep learning are happening on cat and dog data sets and digit recognition data sets, right? For a lot of domains, we just don't have that kind of labeled data set. Tree-based ensembles, perhaps the most famous one that a lot of you have used, random forest. I have my critiques of it and why we shouldn't be using random forest. But they have a lot of promise in machine learning and geographic science. The only catch is to engineer your features well, really model that spatial temporal dependence. And my other thought as always, well, why are we trying on models? Why are we trying to compete with human intelligence by just a model? We can incorporate the human themselves and have better models that are actually used in the real world out there. No offense meant as by the real world. I really meant having stakeholders adopt our models. And lastly, and this was my motivation for the talk too, machine learning is only as good as your labeled data. And interactive visual analytics and dynamic labeling in the context of analysis, if you can do that, if you can have your domain expert do that for you, holds a lot of promise for successful implementation of machine learning. With that being said, I think I am done with my talk. I want to thank you all again for being patient. I know I went a little over time, but I'm going to stop here to take questions.
Thank you, Morteza. That was wonderful. I'd like to open the floor up for questions. Anybody has questions? We have a few minutes. Questions from the audience?
And I'm sorry, I think I went a few minutes over time. I remember you said some people need to leave around.
Some people.
Can I ask a quick question?
Yes, please.
Oh yeah. So I saw you. This is like completely foreign to me. I mean, I don't know about this type of work at all. But you use a lot of different data sources, and I saw some of them were like social media, which I know in my background in international development and public health is also being used as well. But I was just wondering, how reliable is it? I guess, you said things are only as good as the data, and I guess, if you're looking through an academic paper, at least it's been peer reviewed or, written by an expert or something. But when you take the data from things like Twitter and Facebook, like, do you have a way to kind of monitor how, accurate it is? I mean, especially you mentioned yourself, fake media and this type of stuff that people are writing. People can write whatever they want. So
that's a good question, Matt. Yes, we are not drawing scientific conclusions using Twitter data. I am not, we are not, I will circle back to the COVID-19 predictive models. The tool sets that I used showed you were for situational awareness. So we had sometimes, campus emergency operations center staff. They are really short on staff and they want to get a sense of what's going on the ground. We had several festivals in universities where folks wanted to monitor the atmosphere. And the toolset was just made for that, literally that, and try to narrow down the tweets to the ones that they were interested in, or they wanted anomalies to be flagged. But we are not really modeling anything of, value. We don't have, let me put it this way. In this particular case, we did not have a representation issue, right? Because we know for a fact social media is wider, social media is richer, and there's lots of representation problems there too. In the COVID-19 predictive models, to our surprise, again, I'm really surprised, this is submitted for publication, Facebook data, and that is how many people in my county are friends with your people in your county. That is a very, very good predictor. No matter, we only looked at the urban-rural divide, and it still performed better than what the CDC is using now compared to the baseline. So that is the part where I was very worried about the representation of social media in rural counties. But at least in this case, it worked well. I hope that answered your question, but happy to follow up.
Anybody else? I have a question. You were talking about the importance of spatial and temporal lags in the process, that if when you include those add some additional explanatory power that can separate the relevant from the irrelevant. Has anybody employed dynamic modeling like distributed lag structures? Like there's a difference between spatial temporal lag regression analysis, for example, and distributed lag, where you have a weighting. Now I was thinking about as time goes on, you can actually have weights associated with that. And if somebody, like I said, human involvement and using heuristic methods, perhaps updating the weights over time as time wanders on. Because obviously in simple spatial temporal lag models, you're going to continue to create forecasts. You could even do that and then see how well you've done going back in time. But with distributed lag models also, you can attach weights to the parameters to see how important it is if you're a nonlinear type of relationship. So you can have polynomial distributed lags. You can have other types of structures. I wonder if anybody's been using those types of approaches.
That's a really good question. I am with you. Linearity only, I think, exists in our imagination. We try to make things as linear as possible with transformations and try to make inferences. So I think personally, my understanding is the reason we use linear models is for inference and study the effect of X and Y and the significance. But yes, so these COVID models, this is really interesting point you're bringing up. I'm not just looking at the connection of this county to the ones around it. If you see there is connections with others too, and these change over time. And we are deriving that through weekly movements, daily movements of people from county to county, as well as social media connections. So there is a little bit of dynamism there, but not, the part I think that you are referring to is incorporated in the model itself. So this is based on the extreme gradient boosting algorithm, our models that is for COVID-19 prediction models. These are tree-based ensembles, and they are not linear models. So for instance, you have, let's say in your county, you had 20% of people infected, right? It means, and recovered. It means 80% of people remain susceptible. 20 people are less susceptible. So your county as a whole is susceptible. When your 20% changes to 80% infected and recovered, and you only have 20% that haven't caught the disease yet, all of a sudden your county as a whole is not susceptible anymore. You've got herd immunity. And these decision tree-based models are able to model that nonlinearity in collaboration with these changing spatial lags. I wonder if that answered your question.
It did, yeah. I think there is a nonlinearity component then built in inherently to this. So that's interesting.
Yeah, that is, and again, I think they hold a lot of promise if we do them well, and we use these tree-based ensembles with a little bit of thought. I don't have the figure on my slide, but in the preprint linked here, actually we do compare the model for temporal lags only versus spatial temporal lags, and there's clear improvement when we include the spatial temporal lags.
Any other questions for Morteza?
And I'm sorry that I assumed a certain level of involvement and use of machine learning. So I know this talk did not reach a lot of folks.
So I don't have a question, but I would love to email you to get a copy of that syllabus.
I'll be happy to send it to you.
It sounds very good. We're dealing with developing AI curriculum here and a course on machine learning and geospatial data. It would be nice to see how you're addressing it and kind of what approach you're taking. Obviously, you mentioned doing projects, but it would be great to see that if it's okay if I email you for it.
Happy to. I'm happy to share my experience. It was an interesting one.
Cool,
Thanks
thank you.
for your interest. Yeah.
Anybody else question for Morteza?
I assume we don't have questions on the YouTube side. I'm not monitoring that link.
It's about a 20-second lag. Morteza, thank you so much for joining us today at this colloquium. I think you're on the cutting edge of a really important topic. This is just going to explode over the next, forthcoming decade. You're really on the cutting edge of something very, very cool. And I applaud you for this work. Let's stay in touch, and maybe we get some collaboration between our departments, because we want to move in that area, and we want to obviously engage in moving, research in that on AI and machine learning. And again, thank you for this very informative, interesting talk.
Thank you so much for having me, and thank you everyone for staying on. Thanks for the virtual applause, and I do look forward to seeing you in person in the conference or in Florida at some point. If you come to Colorado, let us know. Have a good rest of your week.
Thank you, sir. Keep in touch, okay?
Thank you. Thank you very much, Tim. I'm staying on only in case you you need anything from me. Otherwise, thanks again for having me. I guess we're off YouTube.
And it was an honor and a privilege to have you speak. Thank you, sir.
The honor is mine. The honor is mine. And thank you for the invitation. Sorry that I was not very responsive with the abstract and all of that.
Okay, well, thank you.
I'm sorry. If you had a moment, I wanted to ask you a question.
Yes.
Not to keep you around too much longer, but I wondered what your opinion on utilizing a Bayesian framework within your modeling to include a prior information.
I'm not gonna, yeah, that's a great question. And I wish I knew Bayesian modeling well. I know a little bit. I don't consider myself an expert at all. It has its uses. And like Tim said, that is another area of explosion I find. I think, who knows? I'm more of a, let's try it on this domain and see what kind of result we get. But it's certainly just seeing what's going on, especially on the health side, I want to say. It is definitely worthwhile investing in.
I just wondered. I worked for Jason Blackburn in UF, so we've been utilizing BRTs, and I've been working some with in-law integrated nested Laplace approximation. So seeing how that would be implemented into your direction, that would be.
I want to say something. If you're looking for prediction and you only care about that, machine learning perhaps, well, I don't know how, I hate that they have these bubbles of wording, but you know what I'm talking about. TensorFlow, scikit-learn, they will save you. If you are thinking about inference, especially, and dialing and changing things and see the outcome changes, I think Bayesian just holds infinite promise. But again, I'm no expert. Good luck with what you're doing.
Thank you. Hey, good talking to you. Good talk as well.
Thank you very much for staying on. All right, Tim, thanks again. And I hope to see you around. Stay safe and well.
Morteza, thank you again. Appreciate it.